Our universe is dominated by mysterious and invisible forms of matter and energy. They've yet to be fully understood. They remain more elusive than 80% of our oceans that remain unmapped. And just like the oceans make up the majority of our planet, dark matter and dark energy make up the vast majority of our known universe. Dark energy, the victor over dark matter, accounts for roughly 68% of the universe's total mass and energy. Dark matter makes up 27% of that pie, and the rest, a measly 5%, is all the regular matter we see with space observatories, and the minuscule matter we interact with on a daily basis. Figuratively, the unknown is dark, scary, and full of potential adversary, and it's a drive of mankind to figure it out, to rest assured. Literally, dark energy and matter affect our universe. Question is, how? In this space infinity journey, we'll focus on the black voids of nothingness that zip by when focused on stars and their solar systems. In this space infinity journey, we're taking a look at the space between space to discover how dark matter and dark energy influence our universe. To understand how all this darkness can affect our universe, we'll start off by identifying the differences between dark matter and dark energy. It's stranger than fiction, but the truth is most of our universe is hidden in plain sight. Even more worrisome, we can't see or touch it. However, the consensus of astronomers concur that dark matter slows down the expansion of the universe, while dark energy speeds it up. According to the cosmologist community, dark matter works like an attractive force, akin to a kind of cosmic cement that holds our universe together. It's hypothesized that dark matter does interact with gravity, but it doesn't reflect, absorb, or emit light. Meanwhile, dark energy is a repulsive force. It's a sort of anti-gravity that acts as the engine constantly accelerating the expansion of the universe. Here's the first indicators that dark matter and dark energy have major pull in our universe, and that pun is intended with the literal sense. Back in the early 90s, the theory of the expansion of the universe followed a couple of conditions. Number one, the expansion might have enough energy density to stop its expansion and collapse. Or number two, it might have so little energy density that it would never stop expanding. But overall, the rules of gravity were certain to slow the expansion as time and space expanded. Although the slowing had not been observed, theoretically, the expansion of the universe would eventually slow down. Based off the theories of special relativity set forth by the legendary German-born physicist Albert Einstein, the universe is full of matter and the attractive force of gravity pulls all matter together. Then came 1998 and the Hubble Space Telescope observations of very distant supernovae that showed that a long time ago, the universe was actually expanding more slowly than it is today. So the expansion of the universe has not been slowing due to gravity, as everyone thought. It has been accelerating. No one expected this. No one knew how to explain it. But something was causing it. After mathematical calculations, supercomputer model data, and space telescope observations, theorists came up with three sorts of explanations. Perhaps it was a result of a long-discarded version of Einstein's theory of gravity, one that contained what was called a cosmological constant. Maybe there was some strange kind of energy fluid that filled space. Perhaps there's a flaw with Einstein's theory of gravity, and a new theory could include some kind of field that creates this cosmic acceleration. Theorists still don't know what the correct explanation is, but they have given the solution a name. And you don't have to be a rocket scientist to figure it out. It's called dark energy. More is unknown than is known. It can be considered the cosmic sequel to Plato's allegory of the cave. We know how much dark energy there is because we know how it affects the universe's expansion. But other than that, it is literally a dark mystery. But it's just another enigma for humankind to conquer, since roughly 68% of the universe is dark energy, and dark matter makes up about 27%, while the rest, everything on Earth, everything ever observed with all of our billion-dollar space observatory and travel equipment, all adds up to a mere 5% of the universe. Perhaps dark matter should be called normal matter. After all, matter only represents a tiny fraction of the universe. But let's not digress to philosophy and linguistics. One of the best explanations for dark energy is that it's a property of space. Albert Einstein, the first person to realize that empty space is not nothing, discovered that it is possible for more space to come into existence. And since it can pop into existence, one version of Einstein's gravity theory contains a cosmological constant, which leads us to the second prediction indicating that empty space can possess its own energy. Because this energy is a property of space itself, it would not be diluted as space expands. As more space comes into existence, more of this energy of space would appear. As a result, this form of energy would cause the universe to expand faster and faster. Could it be that the growing dark energy leads to the expansion of the universe? But before we get our heads stuck in the clouds, unfortunately, no one understands why the cosmological constant should even be there. And much less, no one comprehends why it would have the exact value to cause the observed expansion of the universe. But there's another proposition. It's the theoretical basis of modern physics. When it comes to the natural behavior of matter and energy on the atomic and subatomic level, quantum theory of matter is the best resource to resort to. In this theory, empty space is actually full of temporary virtual particles that continually form and then disappear. But physicists ran into a dead end again when they calculated how much energy this would give empty space. The answer came out wrong. And in a crushing manner, it was wrong by a lot. The number came out 10 to the 120th times too big. That's a 1 with 120 zeros after it. It's hard to get an answer that bad. So the mystery remains, and the struggle to understand it continues. But perhaps dark energy is more fluid. Maybe it's akin to a spiderweb network of goo. And this brings us to the other explanation for dark energy. It could actually be a new kind of dynamical energy fluid or field, something that fills all of space, but something whose effect on the expansion of the universe is the opposite of that of matter and normal energy. And that brings us to quintessence. Some theorists have named this quintessence, after the fifth element of the Greek philosophers. Quintessence is a real form of energy distinct from any normal matter or radiation, or even dark matter. But if quintessence is the answer, we still lack substantial evidence as to how it interacts, so the mystery continues. And finally, we revisit the prospect that perhaps Einstein's theory of gravity is not correct. That would not only affect the expansion of the universe, but it would also affect the way that normal matter in galaxies and clusters of galaxies behave. It would mean that a lot of million-dollar supercomputer models are programmed with the wrong variables. But can dark matter fit into the variables that we've been following since Einstein's breakthroughs? Scientists have come up with the composition previously explained with 68% dark energy, 27% dark matter, and 5% normal matter by fitting a theoretical model of the composition of the universe to the combined set of cosmological observations. But, according to observations, there is far too little visible matter in the universe to make up the 27% required to offer prolific explanations. Second, it is not in the form of dark clouds of normal matter, which is matter made up of particles called baryons. Scientists know this because they would be able to detect baryonic clouds by their absorption of radiation passing through them. Third, dark matter is not antimatter, because we do not see the unique gamma rays that are produced when antimatter annihilates with matter. So, we can rule out large galaxy-sized black holes on the basis of how many gravitational lenses we see. High concentrations of matter bend light passing near them from objects further away. But we do not see enough lensing events to suggest that such objects make up the required 25% dark matter contribution. It's another stump in the system, a mystery as deep as the abyss of space itself. It's safe to say dark matter and energy are the literal abyss of space. But mankind will proceed to figure it out, nonetheless. What are your favorite theories for how dark matter and energy affect our universe? Or do you reject the theories altogether? Sound off in the comments section below. After you've hit that like and subscribe button, ring the notification bell and click on these other videos from Space Infinity to keep the space journey continuous.